Okay, so today I want to focus on proving the statement we talked about last time. So first let's talk about class groups and how they relate to CM points. I just did it.
Okay. I just updated this. Okay. Schedule downstairs.
Okay, so let R be some sort of order. In other words, R is a finitely generated ring over Z. Sorry, it's finally generated as a Z module. Over Z, which is integral. So the seventh example to think about is R is the ring of integers in some number field. R could also be some finite index thing inside of that. Okay? Okay, so take K to be the fraction field of R. So then K is some number field. Okay. And then we can define two groups. So the first group, the group, let me call it I of R, is the set of non-zero fractional invertible R submodules of K. Okay? So we'll call this precisely in a minute. And then we're going to quotient that just by the ideals generated by a single non-zero element times R. Okay, a subgroup of principal ideals. Sorry, what am I doing? No, sorry. I of R is this. I'm going too fast. I of R is non-zero fractional invertible R submodules, and P of R is a set of principal ideals. Okay, and then we define the class group of R, sometimes written as pick not of R, because it's pick not of spec R, just as I of R. On P of R. Okay? So to remind you what I of R is, so a submodule of M in K is an I of R if there exists some R submodule N in K with M times N just equal to R. Okay? Alright, so if R is the ring of integers of K, and this is just all finally generated OK subideals inside of K, they're invertible sort of free, and you modify the principal one, you get the class group, and so slightly more generally, you know, this sort of definition. Okay? All right, so now very quickly, let's specialize the case where K is a quadratic field. Okay. Then the world becomes a little simpler. So, OK, the ring of integers of K, so the maximal order inside K. Is just Z joined tau. Well, what's tau? So if we let D be the discriminant of K, in other words, K is Q joined with D. And tau you can choose to be root D plus 1 over 2. If D is 1 mod 4. And root D otherwise. Okay. And then R is an order, and OK is the maximal order, so R is something inside OK. And in fact, we can write R as Z of joint M tau for some N neatly determined as a positive integer. Okay? So now, there's an important fact in this theory that it's easy to miss when we first look at it, but quadratic fields are sort of nicer than the average field in the following way. So if tau inside K is a Z lattice, tau is just a subgroup of K, isomorphic to T squared. Then we can define end of L to be the set of alpha in K star, where alpha times L is inside L. So it's just the endomorphisms of L that you get by multiplying the elements of K. Sorry, alpha and K. There's no meaning this time. I apologize. Zeros in here. So then for free, because this is a Z lattice, this ends up being an order. And L is a subring of the ring of integers. So if this is the case, and K is a quadratic field, then in fact L is an element of I end of L. In other words, L becomes an invertible end of L ideal, or submodel. Okay? So this fact is not true for fields of degree more than 2. Okay, there's no reason for this to be the case. It's certainly true that given any lattice, there's some endomorphism ring of that lattice, and this becomes an ideal. L is certainly an ideal for end of L, one by definition, but there's no reason for L to be invertible. Okay, so in general, to study all lattices, you have to go beyond class groups. You have to study sort of more general and complicated submodules. But for quadratic fields, that's not the case. So by going to the class group of all the suborders, you exhaust all lattices in this quadratic field. Okay. All right. So one other basic fact that we're going to need. We call it theorem of Siegel. The general form is also viewed in Brouwer, but for quadratic field is due to zero, which says that if K is a quadratic imaginary field, so K is cubed root D, B is less than 0, then the size of the class group of K is roughly root D. Given the 1/2, this little whole fun. Okay? So it ends up being important that this is an effective bound. This relates to the famous 0-0 problem, which you sort of can't say exactly how fast. And also famously, you can say exactly how fast you come to literal 1, except for one possible exception. That's kind of annoying.
Take the absolute value.
Yes, sure, thank you. Okay, so more generally, if R is inside OK, is some order, that actually follows pretty quickly from this, that you can generalize the same thing to R. The class group of R is the actual value of the discriminant of R to the power of 1/2 plus level of 1. Okay? You get this pretty quickly from this is by understanding how the class group changes when you pass from the integers to a suborder. And of course, if K were a real quadratic field, you have a similar statement, but you got to include the unit group. And luckily, we're dealing with CM theory. Everything is always totally complex. You know to deal with that. So it makes it here a little bit nicer. Okay, so now to get to the relation between this and CM points, first to tell us a bijection between the union of all class groups over all imaginary orders and all the CM points on the modular curve. Okay, so there's a claim that exists a natural bijection from the union over all R. So R is an imaginary quadratic order. With, let me just write it as x1 CM. Same for what inside x1. Okay. And how does this bijection work? Well, to go this way, you say the following thing. So, suppose that R is an order inside some field K. Okay? And because it's imaginary quadratic, K naturally embeds inside its tensor product with the reals, which is complex numbers. Okay? And suppose that I, you can think of I as being an R, it doesn't matter, is an invertible submodule. Okay, or K, doesn't matter. Okay, then we can think, so then we can consider I, which is inside R, which is inside K, which is inside C, just to be a sublattice, complex numbers. Okay. Okay, so this gives a point I inside the moduli space of sublattices. It's exactly H. Actually, I need to write it the other way, sorry. It's exactly H mod SO2Z. It's the same as Y1, I guess. Okay. So this gives us a point inside Y1 by thinking of I as a lattice. This point is well defined up to changing basis, and so we get a point in the upper half plane in one direction. Moreover, I has extra, C mod I will have extra endomorphisms because R gives you the extra endomorphism, so you get a C. Okay. Let's say you go this way. So now to go back. So suppose that the class of Z in X1 is a C point. Okay? So what does this mean? This means that the endomorphisms of C mod this lattice are strictly bigger than Z. So then you let R be the endomorphism of this lattice. So this is a set of complex numbers such that alpha times this lattice is itself. Okay? So then R is a ring, and it has to be of dimension 2, because it's triply contains Z. Okay. So then if you think of I being this lattice, this is going to be not quite inside R, but it's going to be inside K. So, which is R tensor Q. Again, because endomorphisms are exactly R, and what we said before, I is an invertible R sub 1. Okay? So given the same point, we produce a ring together with an invertible I sub 1. So technically, we haven't checked that it doesn't depend on which actual element Z we picked, but that's not too hard to check, so I'm going to leave that. Yeah, so over here, the fact that I is an invertible R sub module for free is where we use the fact that we're dealing with quadratic fields. Okay. Okay, so it's a nice consequence that to talk about the same point, we can sort of restrict ourselves to static class groups. Which is nice for sort of group theoretic. Whereas if you deal with CM theory for abelian varieties, which we might talk about a very little bit at the end, things get quite a bit more complicated. Okay, so now that, let me call it S sub R in X1 CM be the image of the class group of R. So it's all, you can think of it as all CM elliptic curves, and the morphism ring is exactly R. Then it's a theorem of Shimura. I think this case is Shimura, but the whole thing is about Shimura and Tanyama, so let me put both their names here. So let's do this, and let's let K again be R tensor Q. So Shimura says that the set S sub R is a single orbit under the Galois group, not just of Q, but in fact of K. So Q bar over K. Okay. So all these points are Galois conjugate, which is going to be very important for us because large Galois orbits are sort of the name of the game for the most part. But in fact, we know more than this. So this is true. So moreover, by class field theory, we have a surjection, a natural surjection from this Galois group onto a class group of R. Okay. R and the action of this Galois group on SR, we call this C sub R. So factors through C sub R, and then is isomorphic through multiplication in the class group. So in other words, if you want to know what the action of a Galois group element is, let me call it sigma, times the element of S sub R corresponding to an ideal, I, what you do is you apply CR of sigma to get an ideal class and a class group of R. And you multiply it by I, you take the class of that. Okay? So it's actually, this is already a very strong statement of knowing the single Galois orbit. But in fact, we know more than that. We sort of know what it is. We know what the action is, sort of group theoretically. Group theoretically is just isomorphic to a torsor under the class group of R. Okay? All right. So now, before we talk more about single points, I want to describe this map from here to here a little more explicitly, because it's nice to have more concrete realization of it. So, take I in R to be an invertible ideal. Okay. Assume that I is primitive. Ideal. I is not divisible by the ideal NR, or n equals 1. You can always do this because if there's divisibility, you can just factor it out. Okay, now let A be the norm of I. So in other words, let A be the index of I in R, in the Abelian group. Then because I is primitive, you can show that a basis for I consists of A together with some B plus tau, where tau is an element such that R is the adjoint tau. So it's either root discriminant or it's 1 plus divided by x. Okay. Okay, so the lattice is A plus B tau, and we want this lattice as being inside H minus up to Z. But we're going to do now is we're going to scale it so that this A becomes 1. Okay. Now, the class of I is represented by B plus tau divided by A, thought of as a point in H mod as a loser. Okay? Alright. So of course the hard part is to actually figure out which A's and B's give you ideals. That's sort of why a lot of these are tricky, but still fairly important for them. Okay, so now one thing we're going to use is the note. So if R is Z adjoint tau, where tau is either root D or 1 plus root D over 2, D is a negative integer, then tau, the class of tau, in here is a CM point. Okay? And this guy is very high up in the cusp. Right? So if we look at the fundamental domain we had last time, tau was like up here. So it's either in the middle or it's like shifted off towards this line, depending on whether it's 1 plus that or not. And it's very close to the point infinity. So let's quantify that. So recall that at infinity, Q is e to the 2 by I z is a holomorphic coordinate. Okay? And so now if we look at Q of tau, also Q of infinity is 0, e to the 2 by I of infinity becomes the point 0 in these coordinates. And if you look at Q of tau, and you look at its absolute value, what you get, depending on what tau is you get, if it's this, you get e to the minus 2 pi absolute value of root d, or if it's this, you get e to the minus pi absolute value of root d. Okay? Because by doing e to the 2 pi I of this number. Okay, so this is like extraordinarily small. And the fact that this is the case ends up being useful in many proofs with CF points. If you know that it's sort of, these points, we're going to use this more precisely in the proof, but sort of intuitively, these points aren't all that small, right? They aren't all that close to each other. If you subtract two of these guys, you get something which is at least like 1/d. Whereas this guy is like exponentially close to 0. So that's kind of weird. That ends up being very useful when ruling out phenomena. All right, so let's prove the underscore statement. So proof of unrecorded for x1 squared. Yeah, so we're giving Andre's proof with sort of a bit of tweaking to make it a little bit simpler. Okay, so suppose v in x1 squared is an irreducible curve. Let me say curve, actually, with infinitely many CM points. Again, let's call them sort of xi1 and xi2. The sequence of CM points inside V. Okay. Now these are all algebraic. We explained last time CM points are all algebraic. So for this to be the case, V has to be defined over Q bar. And then again, by combining with defined many of its conjugates, we can reduce right away to the case that V is an irreducible Q curve. Okay? So it's finite U and a finitely many algebraic curves, each of which is defined over some field which is Galois stable. Okay, so irreducible doesn't really matter for us, but whatever. So V is some finite union of curves, which is stable under the Galois group of Q. Okay, so first we're going to do we'll just be Galois theoretic. So we're going to claim that if you look at if you look at the endomorphism rings of these 2 points, they don't have to be the same. They, in fact, don't have to be the same. But they do have to be the same after you tensor with Q. So the quadratic fields corresponding to both of these points are, in fact, the same. Obviously, if I is sufficiently large. Okay. Note, by the way, that we have no assumptions so far. So even if V is a special curve, this is still true. Right? Which checks out. Like if V is a Hecke curve, then in fact, that's for all I. Okay. All right. So what's the idea of the proof? Well, the idea is going to be that the field generated by these two CM points is going to be very different if the quadratic field is not the same. The quadratic fields are different. And that sort of can't happen because they lie on this algebraic curve. Okay? So, proof of claim. So let B in x1 squared be of degree d1 from a d2, okay, which means that the projection of the first coordinate is of degree d2 and the second coordinate is of degree d1. Or if you write to the polynomial, it's the highest power of the first coordinate, the highest power of the second coordinate. Okay. So then Q adjoin the xi1. So then, sorry, I want to change this way. So then xi1 is of degree at most d1 over xi2, and the other one is of degree at most d2 over xi1. Okay? It's sort of easy to think about the polynomials here. So fix the y coordinate, the x coordinate satisfies the polynomial. d1. This thing is true. Okay, so now let K1 be sort of this field. So that whatever, K1 and 2. Be the field we're talking about, and assume K1 is not the same as K2. They're actually two different quadratic fields. Okay. And let L12, L1 and L2 be the field generated by x1 or x2 with that field. Okay? So this is the Hilbert class field over Li is the Hilbert class field over Ki. Now what we wrote down earlier, sort of each x1 and x2 generate the corresponding full Hilbert class field. Okay? Okay?
You want G of x?
Yes.
You want G of x1, x2?
Sorry, I can't
Do you want the J invariant of x1 and x2? Those generate the x.
Yeah, sorry, I'm writing them as points inside x1 squared, so they already are the J invariants. The only piece of notation I have is here. When I write them the more, I mean the corresponding elliptic curve. Otherwise, these guys are already J invariants. Okay, so now we're going to have a field diagram. So let me write, let's see, so let's let L be the combination of L1 and L2. Take K to be a combination of K1 and K2. And let M be the intersection of KL1 with KL2. Okay, so it's a lot of definitions, but once I write the field diagram, it clears it up. So here's the field diagram. We're going to take up most of the blackboard with us. So here we have Q, here's K1, here's K2, and we combine to make K. These degrees are all small, so it's just a biquadratic field. Okay, now K2 gives you L2, and this combines to give K dot L2. K1 gives you L1, Here you get K dot L1. And up here, the join of these two fields is K dot L. And we let M be the intersection of these two fields. Okay? Okay, so importantly, both of these extensions are abelian, and both of these extensions are also abelian, the Galois with abelian Galois group, which means that these two guys are abelian, which means that this whole extension is also abelian. Okay? So K dot L is a big abelian extension of K. And now we're assuming that x1i, we know that x1i is of degree most d1 over this field here, right? And what that amounts to is saying that this extension is of degree at most d1. Because to get this extension from here, all you're going to do is adjoin x1, and that's a small degree over L2. And this extension here is a degree at most D2, right? Which means, because this is abelian, and this Galois group, and this Galois group here is just generated by this one and this one, but this extension is of degree at most D1 times D2. Okay? So the point is going to be that M over K is a very large degree. Because it's of degree at least sort of each one of these divided by something which is at most D1 times D2. Okay? So to get is that Nk is less than or equal to sort of the max of the class group of what we call R1 and R2, where these guys are R1, 2. Divided by its absolute constant D1 and D2, fixed for all existence. Okay? So this extension is still pretty big. Questions about the scheme diagram before we move on?
You mean greater than, right?
I mean greater than. Thank you. Yes. So this is just like a quantitative way of saying that these extensions are almost the same. Right?
Do you
Yes.
really use abelian or you just use Galois?
No, we really use abelian. Because in an arbitrary group, if I give you an element of order D1 and an element of order D2, they could generate the entire group. Right? Like the infinite free group of order 2 is generated by two elements of order 2. In an abelian group, however, that can't happen because everything commutes. So here in a group of order D1 and D2, really generate something of order D1 and D2. Yeah. So no, abelian is very important for this argument to work. All right. So we have this. So now we're going to use what we're going to do to finish. So we're just following. I'm going to call it a fact, even though it's not very hard to prove formally. So if we look at, say, for example, this extension here, so we get an action by the Galois group of the quadratic field K2 over Q. This is a group of order 2. acts on the Galois group of L2 over K2 by lifting and conjugation, and that makes sense because there's a group here is abelian. And this action is the map, the action of the non-trivial element is the map x goes to x inverse. So it's just inversion. Okay? And basically the proof is everything functorial, and this thing is the same as the class group, and the inverse of an ideal is this conjugate ideal. Okay? Alright, so this guy acts by conjugation on this guy via inversion. But this Galois group here is a subgroup of this Galois group, actually. And so, therefore, the Galois group of K over Q acts on the Galois group of KL2 over K by inversion. And therefore, it acts on this focus Galois group also by inversion. Okay? So to get the action of this guy on this guy, you project to this Galois group, and this trivial you keep the same, and this non-trivial is inverted. And M is a subfield, so the same thing is true over here. Okay, now take sigma in the Galois group of K over Q to project non-trivially the Galois group of K1 over Q and trivially to the Galois group of K2 over Q. Okay, this is a biquadratic field, it's Zima2 cross Zima2, so that can be the element 1, 0. Okay? Now the question is, how does sigma act on this Galois group? On the one hand, it projects non-trivially here, and so it acts as -1 on the whole thing, so it acts as -1 here. On the other hand, it projects trivially here, so it acts trivially on this Galois group, so it acts trivially over here. So sigma acts on this Galois group both by inversion and as the identity. Okay? So that can only happen, the inversion can only be the identity if the Galois group of M over K is an elementary 2 group. So is this is isomorphic to Zima2 to the power of R for some number R. So it's entirely true. Okay. Okay, so now for this to happen, this has to be entirely two torsion. Which means that this guy has to have a lot of coordinates as well, which means this guy has to have a lot of coordinates as well. And we're going to show that's impossible. The class groups don't have that much coordinates inside them. So that's the contradiction. Right? So let's do that. So, okay, we're at the point where this thing is a two group. So let's go say over here. So it follows, because this is a quotient of this group, that the two rank of this guy is at least the two rank of this guy, but this guy is entirely two torsion. So it's the size of this whole thing. And what do we know about this size? Well, it's essentially this guy, up to something of order at most d1. So this thing is at least the Galois group of this divided by, say, d1, d2. So as a result, for this to have a chance of holding true, this field must be basically entirely two torsion. Two torsion must be the whole thing up to a factor of d1 times d2. Okay? Okay, but this Galois group is equal to this Galois group, or at most the subgroup of order 2. That's the only thing that can happen. So therefore, we also learned that look at the Galois group of L2 over K2, look at its two torsion, and divide by the whole thing. The index is at most d1 times d2. And another way of saying that is that the class group of R2 is mostly two torsion. Okay. But now we're almost done. Sorry, I'll be finished in like 2 minutes. So because R2 is a quadratic ring, we actually know what the two torsion is. It's just a number of primes, basically. So it's the otherwise is the number of primes of the discriminant of R2 of something which is bigger than 1. Whereas the size of the entire class group by Siegel's theorem that we just wrote down is roughly the discriminant of R2 to the power of a half. Okay, so the square root grows much faster than log, which is already faster than this. So therefore, disk R2 and disk R1 are bounded. And that's a contradiction. Sorry, which part? Oh, 2 to the power of this. Is that what you mean?
Yeah.
Yes, yeah. D is number of divisors. That's right, yeah. Okay, these guys are both bounded, and that gives finitely many possible CM points. Okay? So in fact, maybe just, we'll continue the proof next time. But to get a sense for this argument, a simpler version of this argument, if you apply to Lang's conjecture and a curve in GM squared, will show you that the order of the two torsion points is essentially the same. It's the same up to a bounded factor. The basic idea being if one order is much bigger than the other, then the Galois group permutes this one while fixing this one. And that can't really happen. You can only have so many fibers in an algebraic curve. So this is like an upgraded version of that. Okay, so we'll continue next time. There won't be any class this Friday, so that doesn't look on